Hello, and thank you for joining us on this webinar. My name is Aisha Hortachsu, and on behalf of the Applied Technology Council, I would like to welcome you to the webinar on FEMA P-1026 publication on rigid wall flexible diaphragm buildings and alternate procedure. This webinar is brought to you by the Applied Technology Council under an architect-engineer contract with the Federal Emergency Management Agency National Earthquake Hazards Reduction Program. If you haven't already, you can download the handouts using the link in the chat. We know many of you are interested in receiving professional development hours for your attendance today. For those who registered and attend the webinar, a certificate documenting professional development hours will be sent by email within 4 weeks. If at any time during the webinar you have questions, please type them in the Q&A window that you can open from the Zoom control panel. We are planning to have a live question and answer session at the end of the webinar. Please submit your questions as you have them, rather than waiting until the end to submit them. We will answer as many questions as we can, time permitting, at the end of the webinar. Next slide, please. I would now like to turn it over to Mike Tong from FEMA's Earthquake and Wind Science Branch, who will provide a brief introduction to today's webinar. Mike, please go ahead.
Thanks, Aisha. Hi, everyone. Good morning, good afternoon, or evening, wherever you are. I'd like to join ATC in welcoming you to this webinar on FEMA P-1026. This FEMA report was published in 2021. It is an update to the previous edition published in 2015. FEMA, under the National Earthquake Hazard Reduction Program, also known as NEHRP, has a responsibility to support translation of new knowledge and research results for improving code standard and design practice. This updated report has incorporated recent research and numerical studies on bare steel deck and wood diaphragms. The update has enhanced the alternative procedure developed and published previously. The report has also provided detailed examples to compare the traditional procedure and the alternative procedure. As we all know, rigid wall flexible diaphragm buildings can be seismically vulnerable. Such buildings can suffer severe damage and even collapse, as seen in past earthquakes. Their collapse mechanism is different from those of seismic force resisting systems. A large displacement in the diaphragm can trigger failure, even cause collapse, and such failure mode is not well represented in the equivalent lateral force method for building design. So to address this issue, FEMA sponsored the first study and the follow-up update. The project team, formed by ATC and led by Dominic Kelly, further advanced the alternative procedure in this update. It was shown to provide better building performance and cost-effective. The alternative procedure was approved and included in the 2020 NEHRP recommended seismic provisions for new buildings and other structures, and then adopted in ASCE 722. I'd like to take this opportunity to thank ATC for hosting this webinar, and thanks also to Dominic Kelly for presenting this important topic. Hope you find the webinar valuable and useful to your work, and please let us know if you have any comments, suggestions, feedback. We also have other technical guidance, code resource, and tools for earthquake risk reduction. You're welcome to check at the FEMA website for our recent earthquake publications. So with that, Aisha, I'll turn it back to you.
Thank you, Mike. Now I would like to introduce our presenter today. Our presenter is Dominic Kelly, SE, who is a senior principal at Simpson, Gumpertz & Hager. He has 38 years of experience as a broadly experienced consultant in structural design, repair, and investigation of building and non-building structures. He has extensive experience working on both on the East and West Coasts. In 2021, he was honored with the American Concrete Institute Alfred E. Lindau Award for his outstanding contributions to reinforced concrete design practices in the industry. He has served on the ASCE 7 Subcommittee on Seismic Loads and ACI 318 Committee for over 20 years each, and he continues his participation on the NEHR Provisions Update Committee. Dominic served as the Project Technical Director for the ATC project that developed the FEMA P-1026 publication. I would now like to turn the webinar over to Dominic. Dominic, please go ahead.
Thank you, Aisha. So I'm going to talk about this FEMA P-1026, which is, I'd say, long overdue. It's been well known that rigid wall flexible diaphragms are vulnerable in earthquakes, and I got asked even yesterday, what's taken so long to start considering these buildings as a different building type? Well, we're not quite treating them as a separate building type, but we've now have provisions in ASCE 7 that treat it as at least a different type diaphragm and a building that will be controlled by the behavior of that diaphragm. So the learning objectives for today are to learn why this document was originally created and why it's being updated, why it was updated in 2021. You should become familiar with the contents of what's in this updated FEMA report. You should become familiar with the alternative rigid wall flexible diaphragm procedure as incorporated into ASCE 722, including its limitations of use. I'll also be covering a little bit on how we evaluated this type building using FEMA 695 to develop the procedure, and also to learn how this procedure varies from the traditional procedure used to design these buildings. These buildings are all over the country. You see them, some are quite large, sometimes 1,000 or even 2,000 feet long. Although broken up into several separate structures when they're that long. But they are, if you ever look at an aerial view of a city, you will always find regions where these buildings exist. Okay, some of the shortcomings of the traditional rigid wall flexible diaphragm design approach is that it's based on the equivalent lateral force resisting system, which is based on the response of the vertical elements if it's of a seismic force resisting system. So the shear walls, it doesn't really consider the diaphragm at all. But we do know that from past earthquakes, the primary seismic response is dominated by the deformations of that horizontal diaphragm. And so the equivalent lateral force procedure does not account for this diaphragm deformation. And so we ran some numerical studies using FEMA 695 methodologies and found that the probability of collapse may be greater than what's desired by the building code, by our building code and ASCE 7 in particular. And so this is given these shortcomings, we decided maybe it was time for a new procedure. So the outline of what I'm going to talk about is introductory material summary and a status of the alternative procedure for seismic design. I'm going to provide a description of these buildings, the performance of them in past earthquakes, and potential issues in future earthquakes as we solve the biggest problem with them, which is the wall anchorage. Differences in seismic response of these buildings versus typical buildings. So how they respond differently from a typical multi-story building. An overview of the requirements in ASCE 7, a comparison of the designs using the alternative procedure versus traditional procedures, and then studies justifying the alternative rigid wall flexible diaphragm procedure, just giving you a flavor of what we did, And then recommendations for additional studies and conclusions. There's still much to be determined about these buildings that have not yet been addressed, but we created a framework to get started on these other topics. The second edition team, it was myself, Kelly Cobean, John Lawson, and Ben Schaefer with working groups from Shahab Torabin and Maria Kolayu. And then there were many other reviewers and others who provided input to this project. I just want to recognize the technical committee. And then for the first edition, the principal authors were John Lawson and myself, and there were contributing authors, Andre Filotro and Maria Kolayu, and there were many reviewers that provided very helpful comments. So I do want to acknowledge them, and it's really came out of a different study that we had done for BEAT that was run by Building Seismic Safety Council. So the list of the chapters in FEMA P-1026, there's an introduction, a description of the rigid wall flexible diaphragms and their performance in earthquakes, the traditional design practice examples. So this document has many pages of examples. So you can learn how they're designed in the past and how we hope these buildings are designed in the future. Development of an alternative seismic design procedure. Chapter 5, implementation of that alternative seismic design procedure. So design examples. Check of the diaphragm deflections. Diaphragm deflections are very important for these buildings. And it's very helpful to, well, you really need to check those in order to check the stability of the buildings. Comparisons of the design procedures, that is the traditional procedure and the alternative procedure. Chapter 8 is future studies for design of these buildings, and then conclusions about the overall project. So what are the origins of this procedure? It's really started back many years ago when we noticed that these buildings were very vulnerable in earthquakes, and the focus was always on the out-of-plane wall anchorage. And over time, I'll have a slide in a little bit that shows how the forces increased and how the attachments requirements regarding the attachments changed as well. There were plenty of sort of papers and research done on these and papers also by practicing engineers describing the performance of these buildings and really identifying the link to diaphragm performance. And so there were recommendations for an alternative design. And the other than those recommendations that appeared in some of the papers, there was an incomplete attempt at preparing such provisions as part of the 2000 NEHRP provision cycle. So then in, almost 10 years later, there was a simplified seismic design project that was sponsored by NIBS, and it was run by Building Seismic Safety Council. And that project started around 2009. And one of the project working groups of that project was the Project Working Group 3, which was tasked with creating standalone provisions for rigid wall flexible diaphragm buildings. That eventually morphed into provisions that could be incorporated into the current framework of NEHRP and also ASCE 7, and led to the FEMA projects where we present the results of these studies. And then there was a NIBS project to prepare the 2015 edition of FEMA 1026. So the applicability of the provisions, the procedure applies to one-story buildings with flexible diaphragms and stiff vertical elements. I'll talk a little bit about what other possible buildings you might use the procedure for a little later. Flexible it's for flexible diaphragms, that is nailed wood structural panel diaphragms that are attached to either wood framing or wood nailers. Those wood nailers are most commonly attached to steel bar joists. And then there are also many buildings that are bare steel deck with powder or power actuated fasteners. We usually refer to those as pins, screws, and gauge limitations to meet special seismic detailing requirements. There's also the bare steel decks with welded connectors, which we found are not very ductile, and so you can't meet the special seismic detailing requirements with these, and so we have created a lower R factor for these for such diaphragms. The stiff vertical elements, what we're really thinking about are either cast in place or tilt up or precast concrete shear walls, masonry shear walls. In ASCE 7, it's extended to concentrically braced frames. That's really common, actually. It's been for years in the middle of one of these very large buildings, large footprint buildings. Composite shear wall, steel concrete composite shear walls, steel concrete composite brace frames as well. We'll talk about what's not allowed at a slide to come. So the status, a summary status and advantage of these of this alternative procedure. Summary is the period that for the building, you compute it based on a value that's consistent with the flexible diaphragm rather than the vertical elements of the seismic force resisting system. Which can, especially for the wood frame diaphragms, result in a reduction in forces if you have a very long diaphragm. And so what's going on is the period is long enough to come off of the plateau of the design spectrum. There's an increased diaphragm shear strength at the perimeter region, 10% of the span relative to the strength of the interior portions of the diaphragm. I'll show that in more detail later. And then for ductile diaphragms, the shear demands for the interior regions of the diaphragm are actually reduced. And so we're trying to push the yielding towards the center of the building. It's not going to be in the center of the building, but it's going to start at the transition between this perimeter region and the diaphragm designed for relatively lower forces. Okay, the status is that this procedure has now been incorporated into ASCE 722, which is probably just about getting ready for some states to perhaps adopt the use of the document, meaning ASCE 722. The advantage is really improved seismic performance at the same or sometimes even a reduced cost for many cases. For some configurations, such as long diaphragm spans, that's where you're going to see your cost reductions. And if you're a smaller diaphragm, you're not going to see a cost reduction. It might actually be slightly more expensive, or there will be a shift, I think, in the industry to fewer and fewer diaphragms, steel deck diaphragms attached with welds and moving towards the PAFs and screws. Okay, so then in order to do this for the steel deck diaphragms, you need to follow the special seismic provisions of AISI S400. It's about a wash for many of the diaphragms. So when you get really large, it will be a cost savings for the steel deck as well. The first edition of P-1026 was issued in March 2015. And the purpose of that report was to introduce the alternative procedure for rigid wall flexible diaphragms with wood diaphragms, which would better reflect the seismic behavior and results in better performance compared to the performance of buildings designed using the traditional procedure. At that time, our target audience was designers of rigid wall, flexible diaphragm buildings, but primarily those in the US designing buildings with wood diaphragms, which means the Western US and Southwestern and Western US is where the wood diaphragms are most commonly used for these buildings. In 2021, we updated the report to be consistent with the provisions that were adopted by ASCE 722. We are working with the same individuals. Kelly Cobean was sort of our liaison between ASCE E7 and then being part of our group preparing the updates. So we were consistent. We knew what was coming ahead of time. We had new numerical studies were performed addressing the bare steel deck diaphragms. We had studied the bare steel deck diaphragms as part of that Building Seismic Safety Council studies, part of those studies, but there was a disconnect between the performance of some physical tests and what we were finding with the analyses. So we decided that we put a pause on expanding this to steel decks at that time. Since then, there have been updates. There have been additional research for the steel deck diaphragms to the point where it was time to include them with some limitations. And that was really the limitations that are now in AI-SI S400. So the updates we did updates to the wood diaphragm numerical studies as well to fully reflect the design archetype buildings using the methodology, which was slightly revised as it was incorporated into ASCE 722. We expanded those studies to include architects reflecting a greater variation in wall weight and also to reflect a range of building heights. And we updated discussions of interest to the user, including a series of recommendations for future studies. So the bare steel deck was not allowed in that first edition over concerns about ductility in the connectors and limited number of connector tests. The available testing showed limited ductility and deformation capacity, raising questions regarding the potential performance. So there was the unknowns about the performance at that point in time. So what changed? Some very good research by Ben Schaefer and others that included additional connection testing. I like the way they tested those connections better than the previous connection study, the connection tests that had previously been done. They did a detailed three-dimensional nonlinear response history analysis, which was very valuable and helped us understand how the steel deck diaphragms will behave and how that behavior is different than the wood diaphragms. And then the ductile detailing in AI was introduced in AI-SI S400. That would have been 20 originally, and now it's updated to 2023 version. Okay, the purpose of the report, the updated report that is to present the alternative seismic design procedure for buildings as it's incorporated into ASCE 7. The primary audience is now targets designers of this type of building throughout the US because it includes both wood and bare steel deck diaphragms. Not that bare steel deck diaphragms weren't already being used in the West Coast, but they are predominant. That's the predominant roof diaphragm you use that is used east of the Rocky Mountains. The intention is to convey design principles to these engineers so that they improve the seismic performance of these critical buildings going forward in comparison to how these buildings would have performed using the traditional approach. And these buildings are very important to the commerce of the US. They're distribution centers, they're retail space, they're used for really the economy is running, works around the contents of these buildings. Okay, so this is, I think there are 2 slides where I have found a typo this morning and I changed it. This was spelled W-O-O-D, so that was just an error. So, so the applicability to other situations. So this slide and the next are based on questions that I received from the first time that I did this talk. And so they talked about whether this is applicable to horizontal roof bracing. So I'm thinking tension only bracing. The procedure would not apply to it without further study and detailing requirements. I think that this is actually being worked on. I think at the maybe not to specifically use it with this procedure, but how you address rod bracing in a roof is being addressed through the PUC process at this point in time, the NEHRP Provisions Update Committee. The roof of a multi-story building, we got a lot of questions. No, this procedure is not directly applicable, but it could be adjusted to apply to the roof of a multi-story building. I looked at for a high-tech company back in the late 90s, I looked at a series of buildings that they had for with clean rooms in them, and they had like a 450 to 500 foot spans on them for steel deck diaphragms. That is an example where that roof diaphragm could be used, could be designed according to this procedure. But you just need to make sure that there's no amplification going on from the building below, particularly if the building of the vertical system is not separated sufficiently from the diaphragm. You still may get the majority of the energy dissipation up in this roof diaphragm, but it may be for harder shaking. So you need to consider that. So existing buildings, it's generally not applicable, but by increasing the diaphragm strength at a diaphragm perimeter, you may meet the performance objective. So it's really at a case-by-case basis whether you have an opportunity to apply it to an existing building. C-shaped systems, we got asked about these. It's been a concern of mine for quite some time. They do not comply with section 12.10.4.1, item 5 of ASCE 7, which requires vertical supports on all 4 sides of a diaphragm rectangular segment. So you either need a collector or that distributes the load to a wall that's not directly connected to that diaphragm, or you need to have a vertical element at the middle of the building, at that expansion joint. You need a pair of braces at that expansion joint. Some other thoughts, we got asked about accidental torsion. Accidental torsion is not applicable because it's a flexible diaphragm. It's not required. Vertical seismic forces we got asked about. They will not affect the design of the horizontal diaphragm, but they would affect, could affect the supporting members, especially if they're long span members. Snow loads, the snow loads, you do have to include the mass of this. You need to include some portion of the snow load as seismic mass, FU or greater of a roof load. The flat roof load is greater than 45 pounds per square foot. They say to include 15% uniform design snow load. I know like in places like Massachusetts in the past, we've modified this particular requirement. So you need to check the local building code to confirm that that's still applicable to you. Softer soils. The softer soils are incorporated in a way that they affect the shape and magnitude of the response spectrum. But what we have not done is we have not included the effects of soil springs amplifying the deformations. We didn't study that, but I really don't think for this type of building that that's going to be a significant factor. Given how long the foundation is. Okay, so a description of these buildings. This building on the left is a plant cast walls that are erected. It's in a building right across the street from where I used to work. They're very stiff, rigid elements. Precast and tilt-up concrete is what you most commonly will think of with these walls, but they can also be masonry, especially CMU walls, or cast-in-place walls less commonly. You can use them with concentrically braced frames and composite steel and concrete composite shear walls and frames, which is much less commonly used. You combine that with the flexible diaphragm, meaning a wood structural panel like an oriented strand board or plywood, which is common in the West and Southwest and Pacific Northwest, or more commonly for the rest of the country, bare steel deck, although bare steel deck is also used in the West, Southwest, and Pacific Northwest, particularly for owners of buildings, large numbers of these buildings where they have a prototype that they want to use, and similar prototype they want to use throughout the country. Okay, so the performance in past earthquakes was really focused on out-of-plane wall anchorage. On the left, that's failed walls and diaphragm at the Air Force Base near Anchorage in 1964 earthquake. This building had been designed in 1951 for a design lateral force of 8% G. And the one on the right is partial collapse of a building with a steel deck diaphragm in Yucca Valley during the Landers earthquake in 1992. So the focus really was on diaphragms detaching from the walls, sometimes the walls falling, sometimes the building falling as the roof partially collapsing as a result. So the poor out-of-plane wall anchorage practices, there were problems with cross-grain bending of ledger boards and too low an anchorage force. The there were code changes following these earthquakes. Talk about them a little bit more in the next slide as to when they occurred, but they had explicit out-of-plane wall anchorage design. You have to specifically start designing for that. Cross-grain bending of those ledger boards was prohibited. The wall ties and cross ties that went all the way across the roof were added. The provisions explicitly addressed connection eccentricity, meaning that they had to be concentric. And the concept of subdiaphragms, particularly for the wood frame diaphragms, was introduced. Increases, and then there was big steps in the out-of-plane wall anchorage force design force requirements. And there was also an increase in the minimum width of subpurlins when you had really close nailing spacing. So instead of a 2x purlins, you have to use 3x purlins when the nailing gets too close. To the nail spacing gets too small. So this is an evolution of wall anchorage code prepared by John Lawson. And what you see is that starting back in 1958, we had a design force of around 28% G. And then the San Fernando earthquake came along. We saw some damage in the 1964 Anchorage earthquake. I think that's the first time it was seen that I know of. It probably occurred before that. But after the San Fernando earthquake, where many of these buildings were damaged, provisions for wall ties, cross ties were now required, and no wood cross-grain bending was allowed. So that's about 1973. And then in the 1976 UBC, subdiaphragms, the concept of subdiaphragms was introduced. And then in 1989, the Loma Prieta earthquake occurred. And immediately following that, in the 91 UBC, the seismic forces for wall anchorage increased some more. And then in 97, it went up again, and there were, they introduced minimum subpurlin thicknesses. So now sometimes it was as much as 3 inches. And there are some variations depending on the situation of your actual building that you have to address. So anyhow, the design forces from start to finish are more than they're on the order of 3 to 4 times larger than when this first became on many engineers' radar. So assuming that you had this wall anchorage force in connection solved, we believe other performance issues may come to light. And those potential issues are P delta instabilities of walls and columns if you have too large a diaphragm deflection, effects of building irregularities, irregular shapes, non-parallel walls, wall bump outs. That's very common just for relief. In view, sometimes you have these small bump outs of 4 feet or even less, but that affects how the diaphragm will perform locally. Deformation compatibility at diaphragm to wall connections. I'll talk about that a little bit more later. C-shaped wall systems are the inadequacies in low and moderate seismic regions could come up depending on how consultants design these structures. And then joist rollover in low and moderate seismic regions could be an issue. That's generally not relied upon in high seismic regions. So how does a rigid wall flexible diaphragm building behave relative to that of a typical building? So if you look in the upper left, what you'll see is the walls deflect a small amount and that the diaphragm deflects a larger amount. To scale, it's probably an order of magnitude difference. That delta wall's probably much smaller than it's drawn. And you come up with a total displacement. And that causes the forces, you get the columns and the walls leaning. And so you need to account for whether or not whether the diaphragm has enough strength to restore these elements when the earthquake changes the direction, or does a P delta effect take over? So if you look at a normal building, what you're really concerned with, a typical multi-story building, you look at the roof displacement, it's almost all captured in the vertical lateral system. And in general, the delta diaphragm is negligible and usually not even computed or considered for many of the buildings, even though there are times when perhaps it should be addressed. So the traditional approach versus the alternative approach incorporated into ASCE 7 includes the following aspects. Both approaches are force-based, which is significant. We definitely considered displacement-based alternative designs and chose in the end to stick with a force-based approach because we felt it was easier to incorporate into design practice than a displacement-based approach, which likely would have been standalone provisions or a standalone document for its design. The magnitude of the design forces, the traditional method, it's based on properties of the vertical in-plane elements, so shear walls and braced frames. The alternative procedure, it's based on the diaphragm properties. And since the diaphragm's really what's moving the most, that should be where the focus should be. The period is for a traditional approach, you're using the vertical in-plane elements, and it's based on diaphragm properties for the alternative procedure. The response modification coefficient for traditional approach is just based on the vertical elements of the seismic force resisting system. And for the alternative procedure, we have our diaphragm based on the diaphragm overstrength and ductility. And then for diaphragm yielding, it's not addressed. And in the end regions, we strengthen them to help control where the diaphragm's yielding. We're trying to push it away from the very edges of the diaphragm. So I want to shift now to the ASCE 7, the limitations of it. The limitations for the system, it's for all portions of diaphragms must use rigid wall flexible diaphragm design if you're going to use the procedure. So you can't pick and choose portions of the roof. Wood structural panel diaphragms on wood framing or nailers and fastened in accordance with the American Wood Council's lateral force document. The bare steel deck diaphragms designed in accordance with ASCE S400 and ASCE S310. The seismic provisions are really in S400. The toppings of concrete or other materials, toppings in like gypcrete, etc., or zonalite, that sort of topping is not allowed, not permitted on this diaphragm. It will change the stiffness too much. The horizontal irregularities, reentrant corners are allowed, but you need to be able to, and the reason it's allowed is because you can break it up into multiple diaphragm rectangular segments. This is what you're trying to do is break it up into rectangular segments. Here, a curved wall, that's a non-parallel wall eccentric condition that would not be allowed. I think in reality, you could probably put in a row of lateral bracing at some point and design a portion of the building for using the procedure. But right now it's saying you need to apply it to the whole building or not at all. Okay, the C-shaped wall system is not allowed specifically in ASCE 7. They talk about, so a C-shaped wall system is you have perimeter walls or braces forming a C shape. So the dash line, back-to-back C shapes, without anything along the expansion joints. And so you can envision the only way you're going to get this to work is if you're counting on some rigidity in that diaphragm and accounting for it in your analysis. And I think that this system needs to be looked at in greater detail and studied before provisions, sort of codified provisions would apply to it. Looking at some other limitations, vertical elements have to be concrete or precast concrete or masonry shear walls. I covered this already. Concentrically braced frames, the composite systems. What's not allowed are moment frames and buckling restrained brace frames. And the reason for that is that the period is thought to be too close to that of the diaphragm. And so it would be questionable which is the dominant behavior in an earthquake. So doing a step-by-step design, looking at the comparison of the steps for the design so the next several slides will be the alternative rigid wall diaphragm, rigid wall flexible diaphragm design procedures on the left and the traditional design procedure on the right. They're both force-based, and our thought is that you would most commonly use the optional two-stage analysis of walls. You verify, the first step is you verify that the walls qualify for the alternative procedure by checking the limitations in 1210.4.1. There's no verification for the traditional method. The next is the alternative procedure. You would determine your diaphragm period based on simple formulas that they have that are based on the length of the diaphragm span in feet. So if you had 100 feet, you're going to be 0.2 seconds. You have 1,000 feet, you'd be 2 seconds. For bare decks diaphragms, they're much stiffer than the steel, than the wood wood diaphragms, and so the period is 0.001. I could see over time maybe that would be revised, but we didn't feel that it was worth any more refinement in our studies. For vertical elements, you then use the approximate period using equations 12, 8, 7, 8, or 9, and which are the exact ones you would use for both the diaphragm and vertical elements for the period determination for the traditional procedure. So you're more likely to be up on the plateau if you're using the traditional procedure. Both of them are essentially the equivalent lateral force procedure. The alternative method, you're determining whether the first step is determine whether you're going to meet the special seismic detailing requirements of ASCE 400. Then you'd have a design using R diaphragm of 4.5 for both steel deck diaphragms that meet the special requirements and for wood diaphragms. And then you designed, if you're not meeting the ASCE S400 requirements for special seismic diaphragms, then you need to use 1.5, an R diaphragm of 1.5, which is a pretty big penalty. And that's because these other steel deck diaphragms that's using welded connections do not have nearly the same ductility, as I'll discuss later in this talk. So then you determine the diaphragm force as C sub S diaphragm times the seismic weight. You compare, so that's the formula 12, 10, 15, and then you check using the plateau of the design spectrum, S sub ds over R diaphragm. If you have an importance factor, you have to incorporate it, but it need not be greater than the constant velocity portion of the design spectrum. So S sub d1 over T diaphragm divided by R diaphragm, and incorporate the importance factor if you have to. In comparison, C sub S and V are per section 12.81 for the traditional method. You determine FPX in accordance with 12.10.11. And you're using an R and TA determined based on the vertical elements. Next, you're determining you determine the diaphragm shears. So you create a diaphragm with faceting zones using the American Wood Council's specification, or you use the ASCE S400 for steel and like the SDI's diaphragm design manual or the producer's tables. You amplify the shears in the end region by 10%. I'll show that graphically on the next slide. And that amplification of shear equals a factor of 1.5. You design the diaphragm chords, which is the way we've always designed them, based on the forces without that amplification. And then you design the diaphragm collectors using their attachments to vertical elements for forces amplified by a meganaught diaphragm. For the traditional procedure, you're creating a diaphragm with nailing zones using the same documents. You design diaphragm chords. That's pretty much the same procedure. And then diaphragm collectors, also the same procedure, except for you're using the overstrength factor in accordance with the vertical lateral system that you're designing. Okay, this is the zone, this 10% of the length on all four sides of the diaphragm, the rectangular diaphragm segment that spans between vertical elements. So this, when you're less than 100 feet, long, you just amplify the shear everywhere in the diaphragm. So you need to be more than 100 feet before you can start really taking advantage of the reduction in our diaphragm, our diaphragm of 1.4, 4.5, sorry. Okay, so then looking at the wall shears, where you're using the optional two-stage analysis method, which is really our intention. You determine the wall shears from the mass tributary to the diaphragm using reactions from the diaphragm design. You amplify them by the ratio of R diaphragm to R of the vertical system. You determine, usually your rho is going to be 1. If you have something other than 1, you just use that value. You determine wall shear from mass tributary to the walls using the base shear coefficient based on R and TA. So that's the vertical system. So the mass of the wall stays in the walls, is what we're saying. You determine in the traditional method, you determine the wall shears using the base shear coefficient based on R and TA and the tributary load from the diaphragm. And there's no, because you're using the same R for the diaphragm and for the walls, or the brace frames, there's no need to amplify the forces. Then comparison of deflections. In both cases, you have to calculate the diaphragm and vertical element deflections, respectively. You need to check those deflections to determine whether they're too large or not, and whether they are, you need to amplify those deflections using CD diaphragm or CD of the lateral system. In general, this CD diaphragm is 3 compared to 4.5 I'm sorry, CD for diaphragm, and CD would be is 3 for the diaphragm. And in the traditional procedure, your CDs for an intermediate precast wall, you're going to be CD of equal to 4, which is equal to R of that system. So after you've amplified it, you check your deflection, make sure it's less than the allowed deflection, and you check your drift for P delta stability. And you have to check the deflection and drift for the traditional procedure as well. I don't know that it's always done, though. The top of wall anchorage and cross ties, those are the same for both procedure, no difference. The vertical design elements for buildings and diaphragms. The design, you're permitted to be designed using the two-stage analysis. I've said that several times now. And like the two-stage analysis procedure for a multi-story building, what you're considering is the flexible upper portion of the building and a stiff lower portion. For the alternative procedure, the diaphragms, that flexible portion, and the walls are the stiff portions. The system ASCE 7 does not require an explicit check to determine the difference in stiffnesses for the system. So just looking at our archetype building, or the building we use as an example for the traditional method, and then we're using the same parameters for the alternative method. We're going to look at a building that's 400 feet long and 200 feet deep. So the tilt-up concrete walls are 9 1/4 inches. Top of walls 33 feet, and the top of roof is at 30 feet. And then the roof dead load's 12 pounds per square foot. The structural sheathing is 15 32 oriented strand board. And for the steel option, it's type B deck or wide rib deck, 1.5 inch deep wide rib deck. Okay, so now I'm flipping for previous slides. I was showing the alternative on the procedure on the left and the traditional procedure on the right. I'm now keeping the traditional procedure on the left and the alternative procedure on the right of the slides. The seismic parameters are S of ds equal to 1.0. So high seismicity, but not super high. SD1 is 0.60, risk category 2, seismic design category D, redundancy factor of 1. The wall design is intermediate precast concrete shear wall. So R is 4, omega knots 2.5, and CD equals 4. So those are all down here in the traditional practice. And for the alternative procedure, you have 1.4 for wood structural panels, 1.5 for bare steel deck meeting the special detailing requirements, 1.5 for like welded deck, and then the omega naught of 2 for, that should say, for the diaphragm, but need not exceed R diaphragm, and CD diaphragm is 3. So looking at these things side by side, you might compute the period for the traditional procedure as 0.26. That's almost always going to land you on the plateau, given how short that period is. You have a C sub SW equal to SDS divided by R, and importance factor is 1. You get 0.25. And that controls in both the north, south, and east, west directions. And when you convert it to, since you're only 1-story building, your diaphragm load's going to be the same as the CS for the building itself. So it's 0.25 times the seismic mass, and here I'm just reporting the diaphragm force. For the alternative procedure, for a wood diaphragm, the 0.002 times 400 feet and 200 feet, you get 0.8 seconds and 0.4 seconds. So C sub S diaphragm is the cap using an R of 4.5. So the plateau of the design spectrum is 0.222, and the CS of the diaphragm for the longer span need not exceed S of D1 is 0.6 divided by the 0.8 second period up above, divided by the R diaphragm of 4.5, you get 0.17. And then in the opposite direction, you get 0.33, which is greater than 0.22. So it means that you're on the plateau. So the design forces are 0.167 and 0.222. So the real difference, real advantage is in for forces in the direction, the short direction of the building, or for the longer diaphragm span, you end up with lower forces, and that means fewer connectors. So moving on, this is just the design forces shown as they're applied to the building, dealing with one direction at a time generally. You're looking at the and then converting those into shears down at the bottom. So you have 1653 in one direction versus 1104. Now these are shears that have yet to be amplified in the end region. But what you should gather from this figure is that the forces in the shears in the middle of the middle region of the diaphragm are significantly less than those than those from the traditional system. Then the only difference on this slide is we're now using the amplified shear forces at the end regions. And then, so for the traditional method, you would create nailing zones to accommodate those forces. It's very common for a big building like this to have 6 nailing zones. When you use the alternative procedure, what you'll find is you'll still have a similar zone that's about the same magnitude in the end regions. But assuming that you're long enough that your period's off the plateau, then you still maintain a total of four seismic zones or nailing zones for that diaphragm. So just looking at plan, how that looks, you can see that it's a lot simpler, less changes to the design. You do have a higher, due to that amplification along in this mid region, you have a larger zone. Here it was a zone 2, and here you have to use a zone 3 in that zone. So a little bit heavier nailing along the length. This is just that was a 2 on the slide that you're going to download. That needs to be corrected. I point that out. So the traditional, now looking at an example for bare steel deck, the real difference, the left-hand side's still the same. You end up with 0.25 W, the weight of the seismic mass of the diaphragm. And the walls that they're supporting. And then the period computation for the steel deck diaphragm results in a much stiffer or shorter period diaphragm. So 0.4 and 0.2. So we're at the same 0.22 for when you're on the top of the spectrum, but it doesn't control in either direction. So here your FPX is going to be 0.22 in both directions compared to the 0.25, and that's prior to amplifying them. So you probably have a similar number of connectors, maybe a little bit more than the traditional method. So really you're buying better performance. And is the real consideration. So this is the same diagram I had before, just showing the forces applied. You'd apply them one direction at a time. You would, the shears prior to amplifying. Here, the shear's a little bit lower before amplifying, but much higher once you amplify it. The end regions is much higher once you amplify it. So you need to design for that. So then moving to how you determine the zones for the decking, there's 2 types of decks that are used. The nested deck's real common east of the Rockies, I believe, and it's the only type deck I've ever seen during my practice time in the East Coast. And when I lived in the West Coast, we always used interlocking deck, and it's really about how you overlap them. I think you'll end up with slightly fewer connectors for the nested deck than for the interlocking deck, because you have to have the screws on both sides of that low area, the 2 ends. So there's twice as many connectors there, and so that will be a slightly stronger deck than a nested deck. So another sort of just looking at the nested deck, bare steel deck, using pins and screws in the traditional method, you'd end up with using 3 zones, 18 gauge, 20 gauge, and 22 gauge. These would be steel deck thicknesses for those gauges. The fastener layouts, 36-7 patterns. The limit is a 36-9 pattern in the AISI S400. You're allowed to use self-drilling screws that are number 10 through number 14 for the side lap fasteners. So we're using number 10s and 12s here. And then the number of side lap fasteners, the way this is typically specified in the East Coast is the number of fasteners per span. So the distance between the joists, you'd have like 16. Looking at that now, just for this presentation, I converted this, so that would be 4.7 inches on center, which is closer than what you're allowed. So this probably needs to use number 14 self-drilling screws in order to achieve the capacity that you need, so that you don't get the side laps closer than 6 inches on center. But this is the way you normally specify it. In the West Coast, you normally specify the on-center spacing of the side laps rather than the number of side laps. So looking for the alternative rigid wall flexible diaphragm procedure here, because we have that amplified zone, which makes the shears higher. We're into 16 gauge. We're still 36/7 patterns. We are using some number 14 self-drilling screws and fastener spacings of 6 inches on center to achieve the required strengths. This is just how it looks for the traditional method versus the alternative method. So you actually, there's a chance you'll end up with more zones. And if you want any guidance on how you pick your zones, there's a pretty good book, Roof Structural Design Guide. I think it's published by Volcraft or Verco. It's authored by Pat Bodwell from Verco, which is now owned. They're all owned by Nucor, I believe. That's a good source to use. Just looking at the interlocking deck button punches. So I'm looking at the non-ductile welded connection. What you see is for the traditional method where you're using an RF4, you can come up with 3 zones that would work. And looking at the shears are now 6,000 pounds per linear foot. It's not realistic to construct such a diaphragm. So I don't think I think an outcome of this procedure is welded connectors to the supports are going to disappear in high seismic zones, and you replace them with pins. Looking at that traditional procedure here, we needed to use 3 zones. We likely would try and, in practice, we'd probably try and eliminate that and only go to 2 zones, which is real common for steel decks, or has been up until now. The diaphragm chord forces, you're computing those the same. In the traditional procedure, it's your area steel required is 5.1. So this is for the wood diaphragm, I believe, the wood panel diaphragm, where you get a reduction in force because you're off the plateau of the design spectrum. Your tension's only 110 kips, so you can use this slightly smaller angle for your diaphragm chord. Looking at the wall design, the traditional procedure versus the alternative procedure, you're looking at a force from the diaphragm coming down of 331 kips compared to 248 kips. And so that difference is that the diaphragm force transferred to the walls is lower because you're off the plateau of the design spectrum. This force is amplified to come up for an RF4, though. So that's accounted for in that. So looking at the traditional in the east, so that previous slide was the walls in the long parallel to the direction of load, was for the diaphragm spanning 400 feet. Well, now you reverse that in the diaphragm, you have 400 feet of wall. In this case, what you're really looking at is a force of 608 kips versus 608 kips because you're on the plateau and you have to amplify the forces transferred to the walls by the ratio of the R diaphragm over R of the vertical system. Okay, so then the reason why you need to check the deflection, you need to estimate the deflections, is because deflections allow an engineer to know which elements, walls versus diaphragms, contribute the most to the building's response. It's necessary to understand the P delta or compute the P delta effects. It's also necessary to know the effect on non-structural elements, and also to check for deformation compatibility of the building. One thing that I had thought was that when you lean and you're bending as the diaphragm deflects, you would get a tension, compression, prying action on the connectors, and you may fail them prematurely. I was helped out by a deck manufacturer who pointed out when they looked at this carefully, they found that the deck will often just deform and eliminate or greatly reduce that prying action. And in the final condition, then can move back and forth without failure of the fastener. So it's something you could check. I imagine when you get to a thicker deck, it would become more problematic, less likely to yield. And for a thinner deck, it's almost certainly going to yield. Okay, so then looking at the diaphragm deflection for a wood panel wall, you use the equation from the American Wood Council's document, and it consists of three terms: flexural bending, shear deformation and nail slip, and then cord slip. What you don't have is really anything really related to the actual panel. The panel's really not deforming much. There's also a four-term equation which reduces the deflection by about as much as 30%. So in this case, under the code level loads, it's 4.4 inches. And when you amplify it by CD diaphragm, you end up with 19.4 inches. And it's probably more likely about 10 inches. So this is something that could be refined with time using this procedure. Looking at the wall deflections, what you do is you're assuming a cantilever off of the foundation. You're accounting for both the flexural deformation and the shear deformation, and using I gross, and then you reduce it to an I effective about 0.35 I gross, because there's not much axial load to prevent the cracking. So in this case, you compute an elastic deflection of 0.03 inches. You have to amplify that by the CD factor, so you're at 0.12 inches. So even 0.12 inches to 10 inches is basically 2 orders of magnitude. There's very, very big difference between. So even if you've underestimated the wall deflection due to connection flexibility down at the connector, the wall connector to the foundation, or some movement of the foundation, it's still likely going to be an order of magnitude less than that of the diaphragm. Okay, so then the diaphragm check for bare steel deck, you're using the average shear force. You're using the shear stiffness for your diaphragm zones, and you're just summing up and the length of each zone, and you're just summing up the deformations that you get in each zone. So in this case, we end up with 0.96 inches. When you convert that to the maximum deflection with a deflection amplification factor of 3, you end up at about 2.9 inches. So significantly less than the wood frame structure. So the bare steel deck characteristics of the wood panel diaphragm versus the bare steel deck. The wood diaphragm is less stiff, and so you end up having lower forces. The deformation is primarily at the nails and wood panels, which is very different than the steel deck, which is really a combination of the connection flexibility and the warping and shear deformations in the deck. There's substantial ductility in the nailed connections. There's also substantial ductility in some of the PAF and screw connections. Most of the deformation is shear deformation, with flexural deformations as only a small component. And it's almost all shear deformation for the steel deck diaphragm. Looking at ASCE S400, you have prescriptive methods for the pins and for the screws. And then there's also this method to quantify diaphragm connections through testing or principles of mechanics. That was an important thing to have available, especially for the steel deck diaphragms. Our hope was that some proprietary connectors or connectors in the future, we could easily incorporate it into the design of these steel deck diaphragms, easily incorporate them into the design of steel deck diaphragms. I don't know if anyone's used that method yet to qualify their anchors. So I'm moving into like what the research that we did and the different performance. You can see that the hysteretic behavior of a 10D nail is quite good on the left-hand side, in that you get deformations out to about 1/2 inch before you really start losing the strength. The PAFs similarly go out to about, you've lost some strength here as well, but you can get out to ductile situations out to about 0.5 inches. And compared to the welds, where it's less than a 1/10 of an inch often, in terms of the deformations you can get out of those connections. As I mentioned before, the deflections are smaller, but warping and shearing of the deck panels also contribute to the deflection, whereas that's not the case with the wood panels. So that was a big finding when Ben Schaefer and his group that was studying the steel deck diaphragms were doing their studies.
Dominic, I wanted to make a time check. We have about 2-3 minutes left.
Okay, so I'm going to move ahead. We just evaluated both procedures. The failure mechanism is we were checking for those analyses. We're checking a P delta stability problem, and that's how we determined the failure. We used 22 historic ground motions, numerous archetypes of steel deck in wood diaphragms, wood diaphragm buildings. We study both high seismicity and moderate seismicity. We use the connection database that was available to us. These are just the archetypes for 400 by 400, 400 by 200, 100 by 100, and 200 by 100. You can read the connection types. You can guess what those were based on what I've presented so far. This is one of those design examples for the traditional method is one of our archetypes that we studied. We basically took the connection database, put it into a diaphragm model to get localized springs. We put those localized springs and localized masses into a model. And then we did lumped masses for the wall as well. And we put them through those time histories. And we found that the smaller wood structural panel diaphragm buildings performance groups failed. And both the larger and small bare deck diaphragm buildings performance groups failed. And so both type diaphragms would benefit from an alternative procedure. This is some of the testing that was done by Shahab and Ben. I like the testing because there are multiple fasteners, so they get the results don't include deformations of the deck, or it reduces the deformations of the deck in the test data. They also they had to simplify their panels that they put into their 3D model to simulate the motion. They and basically what they came out of that, their studies, was that you could use the same values, design values, for the steel deck diaphragms if they met the prescriptive seismic detailing requirements as you use for a wood diaphragm, but not if you had welded or button punched connections. This is just an example of the archetype for the alternative procedure that I've already shown this already. This is with the 4 zones. And so designs using all performance groups for the alternative procedures passed. I've talked about all of these items that are in here for the steel already. You can read those on your slides. The bare steel deck, an important thing was the adoption of the S420, the ductile detailing provisions in there. And then recommendations for additional studies. They're applicable. You know, how are these provisions applicable to buildings with lightweight enclosure? So not rigid walls, but with steel bracing systems and other seismic force resisting systems. Irregular plan shapes and abrupt changes along exterior walls and non-parallel walls. There's a lot of buildings with these irregularities, so they deserve some study. The applicability to buildings with mezzanines and multi-story buildings. I touched on that a little bit. The C-shaped configuration, and then the joist rollover for shear transfer. It's probably okay in the low seismic regions, but in high seismic regions, you wouldn't do that. But specific checks to study that would be of value. And the conclusions are that this P-1026 provides the guidance on the implementation of this new procedure. It's relatively simple to use, and it's based on the dynamic response you would expect for the building. And then the collapse assessments demonstrate improved performance. And our hope is that this procedure becomes the required procedure in a future edition of ASCE 7, and that the current disconnect that allows the use of the traditional design procedure with bare steel decks not meeting AISC S400's detailing is eliminated, is our hope, is what will happen. Thank you, Aisha.
Thank you very much, Dominic. And we were finishing right on time. It looks like we have a handful of minutes left for questions. Before we dive into that, I would like to take a moment to summarize a couple important items. For those of you eager to receive your PDH certificate, note that they are only available for those who registered and participated in the live webinar. Even though we will share a recording of this webinar with you, a certificate will not be provided for viewing the recording. You can expect your certificate via email within the next 4 weeks. And due to the large volume of participants, please be understanding that we cannot make exceptions to our PDH policy. So we have collected a handful of questions in the Q&A pod, Dominic. And I also want, before we start, I want to remind everybody that this is only a 90-minute overview webinar. The document itself is available for free download via the links we provided and through the FEMA website. So there's 250 pages of technical detail and all of the appendices that support the technical work that you can review. So with that, I would like to start with some of the general questions. One is that we will upload a corrected set of the handouts because Dominic highlighted a couple typos there. And there's a couple of requests for you to please repeat the name of that book for design of roofs.
It's Roof Structure Design Guide by Patrick Bodwell. And as far as I can tell, I think that it's got Verco's symbol down at the bottom, so I'm not sure. It says Verco Decking Incorporated, so they may be publishing it, I'm not sure.
Okay.
Yeah, they are publishing it. They published it in 2021.
Great, thank you. We received a couple questions about existing buildings. So this was for ASCE 7, of course. Are you aware of any methods being available for existing building evaluation and retrofits?
I don't know. I haven't looked at what's in ASCE 41 in quite some time now. So at the time we were doing it, we looked at it. I don't think that there's a specific procedure, but the concepts of what we're doing may or may not apply to your building. But the way you would apply it is creating a perimeter zone of higher strength to encourage the yielding to be pushed away from the walls.
Great, thank you. We have a question on would buildings with difference in wall heights from one side to the other, say on the hillside, would they need any special designs?
Yeah, you need to look at the forces that you're transferring through at the different diaphragm levels. And you'd also want to look at the deformation compatibility of the two. So in terms of, a smaller portion of a building needs to be attached to a larger portion of a building. You need to, with a certain amount of strength, that's in the early beginning, near the beginning of chapter 12 of ASCE 7, you need continuous ties across there, I think, to hold the two ends together and trying to get them to move together to minimize the damage of the wall. If you really can't, you'd have to look at sort of the pulling in the two directions, pulling on the wall, and you'd have to, check locally what that does to the wall. You probably need to add some reinforcement to make it behave ductily, I would say. So there's, you just need to use your judgment. Your engineer's not, be an engineer, not a technician. So you need to solve that on your own primarily.
Thank you. We received multiple questions about different systems that one could be using. So we received questions about special concentrically braced frames, CLT, shear walls, special precast panels. Do you have any comments about any of these specific systems and how they could be incorporated into the design?
So I'd worry about like the cross-laminated timber walls. If they were rigidly connected, they might work. But if they're, I think that you anchor these down with a fairly flexible connection. And so if you're the key is to have a difference in period of the vertical system and or especially a difference in system or movement between the vertical system and the lateral system. So if you're detailing such that you provide a nice response with a fair amount of movement, it may not be appropriate. But if you have a stiffer condition, maybe you have, some condition where you're holding it down tight, almost post-tensioning it down, and you don't expect it to exceed you don't expect any sort of significant stretching or yielding. It's not yielding, you'd be rocking. If it's not rocking too much and it's a much lower displacement than you get for the diaphragm, then it would be applicable. But you need to check that. You need to have basically a stiffness comparison between the diaphragm and the vertical system. What were the other systems, Aisha, you said?
Special concentrically braced frames.
Yeah, so that's generally pretty stiff, and so that wouldn't be a problem in my mind. The buckling restrained brace frames, you're often tuning those so that they have displacements that are like on the high end, like the same as a moment frame, where the displacements may be controlling the design. those are systems that are going to be moving close to the amounts that the diaphragm's moving. And so those are systems that would not be applicable to. So it's really, you're looking at any other system, Aisha?
Intermediate masonry shear walls, and I think I saw another one about precast.
Masonry shear walls would be stiff. That would be, you wouldn't expect you would expect it to be applicable, and you'd expect it to be applicable to, I think you said special structural walls,
Special precast walls.
precast walls. It's really, you go back to the heart of, are you allowing a lot of movement or rocking of that wall, or is it a stiff enough condition so that the deformations are much less than that of the diaphragm. So I can see, I'd have to check the cases. I'd take it on a case-by-case basis. And we used to have a provision in the first edition of P-1026 where we wanted the deformations for the walls to be less than 1/3 of the deformation of the diaphragm, or the stiffness is another way of saying it. The stiffness is the ratio of the stiffnesses. That was taken out when it went into ASCE 7. But if you kind of use that principle, if you're encroaching on that number, then I wouldn't use it. But if you stiffen up the vertical system such that you maintain that difference in stiffness, then I think it's appropriate to use these other systems.
Great. Thank you so much, Dominic. I think this concludes our webinar. Let me share some final information with our participants. Thank you. Participants, please click the survey link that pops up when you leave. We especially appreciate your input on topics you'd like to see covered in future FEMA webinars. We used to plan our webinar program. And you can learn more about our webinar program on the atcouncil.org events page. We are planning on conducting 3 additional free FEMA webinars this year. Lastly, expect a follow-up email in the coming days with links to the recording, handouts, and the survey again. On behalf of FEMA and the Applied Technology Council, I would like to thank Mike and Dominic for their presentations, and thank all of you for joining us today. This concludes our webinar.